All right, in this video, we begin learning how to evaluate limits. First, recall the limit statement. Limit as x approaches a, f of x equals L. This roughly translates as saying as x approaches a, f of x is going to approach L. So in the last video, we had one particular example of a limit statement, which was the limit as x approaches 2 of x squared equals 4. The idea of this being that as x approaches 2, x squared should approach 4. As another example, maybe one that looks a little bit more crazy, let's do the limit as x approaches 1 to e to the x minus x square root x squared plus 4 over 5 cosine pi x. All right, so let's say we want to find what this limit will equal. So as x is approaching 1, it would make sense that e to the x would approach e to the 1. Likewise, looking over here, we know that this x is going to be approaching a value of 1. Likewise here, x is approaching 1, so this should be about 1 squared. And then plus 4. And then down at the bottom, if x is approaching 1, then we should be getting cosine of pi in the denominator like that. And then if we simplify this, we're going to get 2e minus square root of 5. And cosine of pi is negative 1, so that's going to be negative 5. Okay, so this last example, it might have seemed a little bit pointless to you perhaps, because all I'm really doing is I'm just plugging in 1 for x to get the answer. And that's kind of how both of these examples have worked. To get the value of the limit, all we really have to do is plug in whatever x is approaching, and we get our answer. But of course, not every example is so straightforward. So let's take a look at a more complicated example. So I'm going to do the limit as x approaches 0, 1 over x squared. So if we simply plug in 0 for x, we're going to get 1 over 0. Now, division by 0 is undefined, so 1 over 0 can't be the answer. It doesn't make sense. So how can we determine what this limit actually equals? Now, when you're confronted with a limit that you don't know how to evaluate, there are a few things that you can do to at least get some idea as to what the limit is. So one thing you can do is look at a graph of your function. So in this case, we have the function f of x equals 1 over x squared. So if you were to graph this function, you would find that its graph looks something like this. Okay. And when we look at the graph, what we see is that as x is approaching 0, whether we approach 0 from the left or the right, the function is shooting upwards towards positive infinity. So hence, based off the graph, we could conclude that the limit as x approaches 0, 1 over x squared, is infinity. Okay, so that's one thing that you can try to do to get some idea as to what the limit is equal to. Another option that you have is to plug in some values for x. So in this example, since we were doing the limit as x approaches 0, what we can do is plug in some values of x which are close to 0. So for example, I'm going to start by plugging in maybe something like 1 over 100, something kind of close to 0. Okay. So if x is 1 over 100, then x squared is going to be 1 over, should be 10,000. And so then if we look at 1 over x squared, it's going to be 1 over 10,000. And remember, when you divide by a fraction, you can rewrite that by multiplying by the reciprocal. So we'd have 1 times 10,000 over 1, which would just be 10,000. All right, so if x is 1 over 100, then 1 over x squared is 10,000. Now let's see if I pick a value for x which is even closer to 0. So instead of 1 over 100, suppose I do 1 over 1,000. Okay. So I'm choosing something closer to 0 to see what happens as x approaches 0. So if you go through everything once again, plug in 1 over 1,000 for x, you're going to get 1 over x squared to be 1 million. Okay. So here what we're seeing is as we plug in values of x which are closer and closer to 0, 1 over x squared is getting bigger and bigger, and it's sort of blowing up. And so hence you can sort of conclude once again, it seems that the limit as x approaches 0 of 1 over x squared is going to be infinity. Now a third method of sorts is really to just kind of think intuitively about the problem. Okay, so here's what I mean. Since x is approaching 0, we can treat x as being really close to 0. in which case, x squared should also be really close to 0. And then thinking about what happens when we divide 1 by something really close to 0. And so when we divide 1 by something really close to 0, we sort of know that it's just going to blow up and get really big. And hence you would sort of make the same conclusion that the limit as x approaches 0 of 1 over x squared is infinity. So this third method, if you will, it's basically the same as the second method, except you're not actually going to plug in any specific values for x, but rather you're just sort of thinking through what would happen if you did plug in values for x, if that kind of makes sense, all right? You might not be able to think intuitively about problems, at least not yet, but hopefully as you become more experienced and get more practice, you will develop some intuition, which can then help you in thinking through some problems. So this was an example where our limit was infinite. We're going to come back to infinite limits, such as this one, later in this workshop series. Now, you won't always be able to easily visualize the graph of a function, and plugging in values for x can be rather time-consuming, and it won't always be easy to think intuitively about the problem. Hence, we want to develop some techniques for evaluating limits. Now, there is no one technique that will work for all limit problems. Rather, the techniques that we develop are going to be useful only to certain types of limits. So before we go over our first technique, let's take a look at an example in which it could be applied. So let's consider the limit as x approaches -2 of x plus 2 over x squared minus 4. If we plug in x equals -2, so -2 plus 2 would be 0. And then in the denominator, -2 squared is positive 4, minus 4. We're going to get 0 in the denominator as well. Again, division by 0 is undefined, so 0 over 0 can't be the actual answer to the problem. Now, if we try to think intuitively about this problem, okay? Let's do that for a moment. So we understand that if x is approaching -2, in your numerator, x plus 2 should be really close to 0. So in your numerator, you're going to have something really close to 0. I'm just going to write like approximately 0 for that. Now, similar in your denominator, if x is close to -2, x squared should be close to 4. And so your denominator is also going to be close to 0. So if we try to think what happens when we divide something really close to 0 by something really close to 0? The answer to this question is not so straightforward. So just some examples, right? Maybe in my numerator, I've got something like 1 over 100, which we think is pretty close to 0. Maybe in my denominator, I've got something like 1 over 1,000, which we also think is pretty close to 0. But if we compute what this is, we're going to that's equal to 10. Okay. All right, but on the other hand, I could maybe just have something like 1 over 100, something close to 0. Maybe if I divide by something close to 0, like 1 over 100 again, I'm just going to get 1. And so you see, 1 and 10, these are not very similar to each other. So if you just have something close to 0 and you divide it by something close to 0, you can't really say what the result is going to be. So because it's not really clear what the answer may be, from this sort of crude method of thinking intuitively about the problem, we refer to 0 over 0 as an indeterminate form. Okay. So we see that it's indeterminate because we can't determine the value of the limit from simply observing that we get 0 over 0. Now, I feel like this example or this video is already running a little bit long, so I'm going to come back to this example in the next video. In the meantime, I want to look at just a small series of much simpler problems. So if I think about the limit as x approaches 0 of x over x, and then let's do the limit as x approaches 0 of 2x over x. Now, in each of these examples, if you just try to plug in 0 for x, you're going to get 0 over 0. Okay. But of course, if you have x over x, we know that we can simplify that and just cancel out the x's. That would just leave us with the number 1. And 1 is just a constant, so it doesn't really matter what x is approaching. It's just going to be always equal to 1. And similarly, when we're looking at the limit as x approaches 0 of 2x over x, same thing, if you cancel out the x's, you just find the answer should be equal to 2. And of course, I could have changed this number 2 to any other number, and then I would have gotten a different answer for the limit. So if I had 3x over x, it would be 3, and so forth. So what this kind of shows you is that if you do get 0 over 0 in a limit, then really the actual answer could be anything. All right, so again, that's why we call it an indeterminate form, because you can't determine the answer just from seeing that you get 0 over 0. So I just want to wrap up this video, and then in the next video, we're going to work through this example here, plus a couple other examples as well, right? But wrapping things up, if you want to evaluate limit as x approaches a of f of x. First thing you should do is just plug in a for x and see if you get a number out of this. Usually that is going to be the answer. Example being like if you have, limit as x approaches 2 of x squared, just plug in 2 for x, the answer is 4. If you get 0 over 0, when you plug in a for x, then you've got to do a bit more work. We're going to, again, examine that more closely in the next video. All right, so I'm going to end this video at this point. Thanks for watching.